The entire planet's advance warning for a solar storm that could take down power grids, crash satellites, and black out GPS runs through a single spacecraft. It weighs 570 kilograms, roughly a grand piano. It was designed for a 5-year mission. It has been operating for 11, and it spent 7 years in a warehouse before anyone decided to launch it. That satellite is the only thing standing between a Cannibal Coronal Mass Ejection, 2 storms merged into one, carrying a magnetic field that rotates and reverses unpredictably, and an infrastructure system that was never designed to survive the compound blow it delivers. If the idea that 2 solar storms can merge in transit and hit Earth as something worse than either one alone got you locked in, take a second and hit subscribe to Orbital View. We're tracking Solar Cycle 25 as it tears through predictions that were wrong by a factor of 2. Drop a comment with your region and whether your power grid has ever flickered during a geomagnetic storm. I read every one. Here's where this investigation goes. A satellite parked 1 million miles from Earth that gives us somewhere between 15 and 60 minutes of warning, and why that window is shrinking. The night in 1989 when 6 million people went dark in 90 seconds, and the physics that made it happen hasn't changed. The January 26th G4 storm that NOAA didn't see coming at the strength it arrived, and why the word cannibal isn't a metaphor. It's a mechanism, and it breaks the single biggest assumption baked into every geomagnetic storm response plan on the planet. Let's get into it. Teal, Duck, Part 1. The storm that swallowed another storm. Right now, and I want you to hold this, Solar Cycle 25 is supposed to be winding down. That's what the model said. That's what the forecast panels projected back in 2019 when NASA and NOAA convened their joint Solar Cycle 25 prediction panel and told the world this would be a modest cycle, peaking around a smooth sunspot number of roughly 115 sometime in 2025. A gentle hump, nothing dramatic. The sun didn't read the memo. By mid-2024, the smooth sunspot number had blown past 200, nearly double the official consensus forecast. The prediction wasn't just off. It was off in the direction that matters most, the direction that means more flares, more coronal mass ejections, more complex eruptions stacking on top of each other in tighter windows. And the sun kept pushing. In February of 2026, a site that tracks solar cycle progression at the Royal Observatory of Belgium, the Solar Terrestrial Center of Excellence, reported that the strongest flares of the cycle included an X9 on October 3rd, 2024, an X8.7 on May 14th, 2024, and an X8.1 produced on February 1st, 2026 by active region 4366. That last number matters, because AR 4366 didn't just fire one shot. According to NOAA's Space Weather Prediction Center, from the moment region 4366 emerged on January 30th, 2026, it produced 21 C-class flares, 38 M-class flares, and 6 X-class flares. Spaceweather.com called it the most active sunspot of Solar Cycle 25, putting out 5 X-class flares in only 2 days with no signs of slowing. When space weather forecasters start calling a sunspot region a solar flare factory, something unusual is happening. And what that unusual thing produces when eruptions launch in rapid succession from the same region is the phenomenon at the center of this investigation. So here's the mechanism, and I'm going to explain it the way it actually works before I hand you the jargon. Think about what a hyperactive sunspot region actually does. It erupts. And then, because the magnetic tension that caused the first eruption hasn't fully resolved, it erupts again, sometimes hours later, sometimes the same day, and because these eruptions launch from the same patch of solar surface, they travel down roughly the same corridor of interplanetary space. That matters. Because what happens next depends entirely on the speed difference between the first eruption and the second. Picture a highway at night. A slow truck pulls out. 1 billion tons of magnetized plasma expanding outward from the sun at maybe 300 to 400 kilometers per second. That's a standard coronal mass ejection. It's enormous, it's charged, and it's heading toward Earth. Normally, that's the whole story. One truck, one trip. It arrives in 2 to 4 days. The magnetosphere flexes. Maybe you get some aurora at high latitudes. Maybe a power grid operator in Scandinavia has to adjust voltage. One event, one response. Manageable. But now picture a second vehicle pulling onto that same highway a few hours later. Faster, heavier, doing 1,200, maybe 1,500 kilometers per second. It's not going around the first truck. It's going through it. And when it catches up, it doesn't just bump and pass. It absorbs. The faster CME consumes the slower one, sweeps up its plasma and magnetic field, tangles the field lines of both eruptions into a merged structure that is bigger, more energetic, energias. This is the critical part. More magnetically chaotic than either parent was alone. That's a Cannibal CME. NASA's Scientific Visualization Studio has modeled the process in detail. The second ejection overtakes and assimilates the first, and what comes out the other side is what researchers call complex ejecta, used a cloud with a larger and more tangled magnetic profile than any single CME. And those complex ejecta clouds trigger protracted geomagnetic storms when they envelop Earth. Not just sharper, not just stronger, longer, more erratic in their magnetic orientation, harder to predict in terms of ground-level impact. And here's the part that makes this more than an interesting astrophysical curiosity. Every space weather response plan on this planet, every grid operator's playbook, every satellite operator's shielding protocol, every aviation authority's polar route decision tree list was designed around the assumption of single event storms. One CME, one arrival, one magnetic signature to read and respond to. A Cannibal CME breaks that assumption at the root. It delivers a compound magnetic punch with internal structure that can flip orientation mid-storm. The models that predict how bad a storm will be require knowing the direction of the incoming magnetic field, specifically whether it's oriented southward, which is when it couples most violently with Earth's own magnetic field. In a Cannibal CME, that orientation isn't stable. It rotates, it reverses. It's a lock that keeps changing the combination while you're trying to pick it. And the people trying to pick that lock have somewhere between 15 and 60 minutes to do it. Part 2. What January 19th told us. I want to walk you through what happened in January of this year, because it is precisely the kind of event that reveals the seam between what the warning system is designed to handle and what the sun is actually delivering. On January 19th, 2026, a halo CME, meaning one that appeared to expand in all directions from the sun's disk, which is the telltale signature of a head-on trajectory toward Earth, arrived and slammed into the magnetosphere. NOAA's Space Weather Prediction Center confirmed that G-force severe geomagnetic storm levels were first reached at 2:38 in the afternoon Eastern Standard Time, datis 1938 UTC. The KP index hit 8. For context, the NOAA scale tops out at G5, KP9. This was one notch below the worst classification that exists. But the number alone doesn't tell the full story. Pull up the 3-day forecast product that SVPC issued on January 21st at 0030 UTC. It's public, published in plain text at services.svpc.noaa.gov. And look at what the forecast team actually projected. The greatest observed KP in the prior 24 hours was 8. The greatest expected KP for the next 72 hours was 6.67. And the rationale line in that forecast is where the real information lives. It reads, G1 through G3 geomagnetic storms are anticipated on January 20th through 21st due to continuing coronal hole, high-speed stream influence, and the passage of a halo CME that arrived late on January 19th. 2 words in that rationale demand your attention. Continuing and influence. A coronal hole high-speed stream, a sustained river of fast solar wind pouring from a gap in the sun's corona, was already washing over the magnetosphere when the discrete CME impact landed on top of it. The storm wasn't a single blow, it was a 1-2 combination, and the observed KP of 8 exceeded what the models anticipated for the combined disturbance. That compound stacking, a sustained stream plus a discrete CME, is structurally analogous to what a Cannibal CME does internally. Multiple sources of magnetic disturbance, overlapping in time, producing a combined geomagnetic effect that exceeds what either input would produce alone. January 19th wasn't a Cannibal event, but it was a preview of the physics. It showed what compound arrival looks like, and it showed that the forecast can come in low when the compounding happens. And that gap, observed 8, forecast 6.67, isn't something you shrug off. At G3, NOAA's own scale descriptions say you can expect voltage correction required on some power systems and possible false alarms on protection devices. At G4, the language shifts. Widespread voltage control problems. Some protection systems will mistakenly trip key assets offline. Spacecraft may experience surface charging and tracking difficulties. High-frequency radio propagation may be degraded for hours. Those are different operational worlds. Grid operators make load-shedding decisions based on these forecasts. Satellite operators adjust orientation based on them. Aviation authorities route transpolar flights based on them. The people at PJM, the regional transmission organization that coordinates electricity flow across 13 U.S. states, have a geomagnetic disturbance operating procedure that's triggered by the forecast severity level. When the forecast says G3 and reality delivers G4, every downstream decision built on that forecast is calibrated to the wrong threat, not by a dramatic margin. But at the edge, where transformers saturate and protection relays trip, a one-level miss can cascade. And consider what January 19th actually demonstrated about compound arrival physics. The coronal hole high-speed stream had been running for days before the CME hit. That stream was pushing the magnetosphere, bending it, preloading the system with sustained pressure. When the discrete CME arrived on top of that sustained flow, the magnetosphere didn't start from a resting state. It was already flexed, already stressed. The CME was the second blow on a system that hadn't recovered from the first, and the resulting KP overshoot tells you that the interaction between the two inputs was nonlinear. The combined effect exceeded what you get from simply adding their individual contributions. That nonlinear compounding is exactly what Cannibal CMEs deliver, except packed into a single merged structure instead of arriving as two separate streams. The physics doesn't care whether the compound arrives in sequence or pre-merged. The grid feels both. That's what Quebec taught us. And that lesson sits underneath everything that comes next. Part 3, the machine at the edge of nowhere. Before I go deeper into the history, you need to understand the warning system. Because everything that follows, every historical case study, every compound scenario, every projection about what a Cannibal CME could do rests on one question. How much time does the planet get between knowing a storm is inbound and the storm actually arriving? The answer is 15 to 60 minutes. Sit with that for a second. 15 to 60 minutes. That is the buffer between detection and impact for the entire planet. 1,000,000 miles from Earth, parked at a gravitational balance point called Lagrange point 1, the spot in space where the sun's gravity and Earth's gravity cancel out so a spacecraft can orbit there without constant fuel burns, sits DSCO-VR, the Deep Space Climate Observatory, launched by SpaceX on a Falcon 9 rocket from Cape Canaveral on February 11, 2015. It weighs about 570 kilograms, roughly the mass of a grand piano, and it is NOAA's primary operational deep space satellite, the nation's first, and the frontline system for warning Earth about incoming solar storms. DSCO-VR carries a suite of instruments, a magnetometer to measure the magnetic field of passing solar wind, a Faraday cup to measure the speed and density of charged particles, an electron spectrometer. When a CME washes over Discover at L1, those instruments register the disturbance. The data transmits back to Earth at the speed of light. But the CME itself is right behind the data, moving at hundreds or thousands of kilometers per second, and the 1,000,000-mile gap between DSCO-VR and Earth translates, depending on the speed of the incoming plasma, to somewhere between 15 minutes and 1 hour of warning. NOAA's National Environmental Satellite, Data, and Information Service states this explicitly. From the L1 point, DSCO-VR can typically provide 15 to 60 minute advanced warning before a storm reaches Earth. The Harvard-Smithsonian Center for Astrophysics describes the same geometry. Solar wind reaches DSCO-VR between 15 minutes and 1 hour before it reaches Earth. That is not a classified assessment. That is the publicly stated capability of the system. Now think about what happens at the fast end. A Cannibal CME that's merged and accelerated, moving at 1,500 or 2,000 kilometers per second, the speeds NASA's Stereo spacecraft measured in the 2012 event, dizzying compresses that window. Hard, you could be looking at 15 minutes or less, and in those minutes, a grid operator at a regional transmission organization has to receive the alert, interpret the magnetic field data, decide on a load reduction strategy, coordinate across interconnected utilities, and execute switching operations on a system that may span half a continent. DSCOVR was designed for a 5-year mission. It has been operating for over 11 years. It succeeded the Advanced Composition Explorer, ACU, which held the L1 Sentinel position before it. And I need to tell you the history here because it matters for understanding how thin this margin really is. The original DSCOVR satellite was proposed in the late 1990s as a NASA Earth science mission. Political priorities shifted. The mission was canceled. The spacecraft was built, tested, and then placed into a storage facility in 2001. It sat there for 7 years. In 2008, a review committee determined that this mothballed satellite was the optimal solution for meeting NOAA and U.S. Air Force space weather requirements. They pulled it out of storage, refurbished it, and eventually launched it in 2015. The satellite that guards the planet's warning window spent nearly a decade in a warehouse, and it is now operating more than double its design life during the strongest solar cycle in 2 decades. Let me put that in concrete terms. When DSCOVR detects an incoming CME, the data flows to NOAA's Space Weather Prediction Center in Boulder, Colorado. Forecasters there issue alerts, geomagnetic storm watches, warnings, and alerts on the G-scale. Those alerts propagate to grid operators, satellite controllers, airlines, emergency managers. But the chain only works if DSCOVR is online, if its instruments are calibrated, and if the data reaches Boulder in time. In May of 2024, during the G5 extreme storm, the strongest since the 2003 Halloween storms, with a KP index of 9 and a DEAST of negative 412 nanoteslas, DSCOVR was the satellite that saw it coming. The CMEs from active region 3664 arrived, and DSCOVR's instruments measured the interplanetary magnetic field swinging violently southward. That data gave SWPC the confirmation to escalate their warnings in real time. Without that L1 measurement, the storm forecast would have relied entirely on solar observations and propagation models, which, as January 26th reminded us, can come in low. I am not saying that to create alarm. I am saying it because the gap between the threat and the infrastructure monitoring that threat is wider than most people realize. And that gap gets wider, not narrower, when the threat is a Cannibal CME moving at maximum speed. Think about what has to happen inside that window. A forecaster at SWPC in Boulder sees the data spike on the real-time solar wind display. They confirm the CME shock arrival. They draft a geomagnetic storm warning, the severity level, the expected duration, the affected latitude bands. That warning goes out through NOAA's alert system. A grid operator at a regional control center receives it. They assess their system state, GASU, current load, transformer temperatures, available reserves, which lines are most exposed based on geology and orientation. They begin executing protective actions, reducing power transfers on vulnerable interconnections, bringing up additional reactive support, potentially shedding load in anticipation of GIC-driven transformer saturation. All of that in 15 minutes. On a good day, with a well-rehearsed team, it's possible. On a night shift with a skeleton crew, during a compound event with magnetic field behavior that doesn't match the playbook, those 15 minutes can feel like 15 seconds. And that is the context for everything you're about to hear in the next 3 sections of this investigation. The physics of Cannibal CMEs doesn't just produce bigger storms. It produces storms that compress the decision window, confuse the magnetic field readings, and deliver internal transitions that existing response plans weren't designed to handle. Part 4. 90 Seconds in the Dark. March 13th, 1989, 2:45 in the morning. Quebec. The temperature is well below freezing, and 6 million people are about to lose power in the time it takes to brush your teeth. I want to take you inside this event because it is the single most important case study in space weather history, and the way it unfolded tells you almost everything you need to know about why Cannibal CMEs are a different category of threat. In early March of that year, the sun was in a ferocious mood. Solar cycle 22 was running strong, far stronger than the current cycle, in fact, with sunspot numbers that dwarfed what we've seen in 25. Active region 5395 was one of the largest sunspot groups observed in decades, spanning an area visible to the naked eye through eclipse glasses. On March 6th, it unleashed an X-15 class flare, a classification so extreme it remains one of the most powerful flares ever recorded. Over the following days, it continued erupting. Let me take you through the sequence because the mechanics matter. The critical pair arrived on March 10th and 12th. Two massive coronal mass ejections launched in succession. The first flare was classified X4.5, the second M7.3, but the classification doesn't capture what made this pair dangerous. It was the sequence. The first CME plowed into the ambient solar wind and cleared a corridor, reduced the drag that normally decelerates a second ejection. The second CME, traveling through that cleared path, arrived at Earth carrying more energy than it would have on its own. This is the same physics that drives Cannibal CMEs. First event conditions the medium. Second event exploits those conditions. Different decade, same mechanism. When the storm slammed into Earth's magnetosphere, the magnetic field compressed and then released with violence that registered on magnetometers worldwide. Geomagnetically induced currents, GICs, began flowing through the ground. And here's where Quebec's geology became the story. The province sits on the Canadian Shield, an enormous formation of Precambrian igneous rock that is deeply electrically resistive. The currents couldn't dissipate through the rock the way they could through more conductive geology elsewhere, so they found a better conductor: the 735 kilovolt high voltage transmission lines of Hydro-Quebec, the lines that carry power from the James Bay hydroelectric stations down to Montreal and Quebec City. Dr. David Boteler, head of the Space Weather Group at Natural Resources Canada, called what followed the biggest geomagnetic storm of the space age. It became, in his words, the archetypal disturbance for understanding how solar activity can cause blackouts. Harmonic distortions flooded the system. Transformers began saturating, drawing huge reactive power loads that they weren't designed to sustain. Static compensators tripped, and then the cascade began. At 2:45 a.m., the storm tripped 5 transmission lines from James Bay simultaneously, causing a generation loss of 9,450 megawatts, against a system load of 21,350 megawatts. That loss was fatal. The James Bay network collapsed in less than 90 seconds, not 90 minutes. Seconds. 21 gigawatts of supply gone, 6 million people in the dark. The Montreal Metro shut down in the middle of morning rush. The airport closed. Schools, hospitals running on backup generators. Businesses dark for 9 hours. And the cause was a sequence of solar eruptions 93 million miles away that had arrived in a compound configuration the grid was never stress tested against. But here's the detail I cannot get past, and it's the one that ties this directly to the Cannibal CME investigation. Boteler's 2019 paper in the journal Space Weather, a 21st century view of the March 1989 magnetic storm, makes something explicit that most coverage of this event gets wrong. The Hydro-Quebec blackout did not occur at the peak of the storm. The DST index, which measures the depression in Earth's magnetic field during a geomagnetic storm, reached its most extreme value later. The grid failed early, during a sharp magnetic transition, a sudden swing in the field's rate of change. Read that again. The grid didn't fail under the strongest sustained pressure. It failed under the fastest change. And Cannibal CMEs, with their complex internal magnetic structure, multiple flux ropes tangled together, field orientations rotating unpredictably, are engines for producing exactly that kind of rapid transition. Multiple reversals packed into a single event window. The grid isn't just facing a bigger hammer. It's facing a hammer that changes direction while it's swinging. After the blackout, Quebec invested approximately $2 billion Canadian dollars over 6 years hardening the system, recalibrated protection trip levels, built a real-time magnetic storm monitoring system, changed operating procedures to reduce power flow, and suspend major switching during disturbances. Hydro-Quebec says those measures have worked. Intense storms have occurred since 1989 without causing blackouts on their grid. But the question isn't whether Quebec is better protected. It's whether the rest of the world has done the same work. In the United States, the Federal Energy Regulatory Commission, FERC, has introduced mandatory reliability standards for geomagnetic disturbances. That's real. That's progress. But the capital investment required to actually harden the most exposed high-voltage transformers across the grid has been, in the assessment of multiple analysts, considerably more limited than what Quebec undertook. The transformers most vulnerable to GIC saturation, the extra high-voltage units, the ones that take 18 months to 2 years to manufacture and replace, are concentrated in regions with resistive geology that behaves like Quebec's Canadian Shield. Parts of the Appalachian region, parts of the upper Midwest, areas where a severe geomagnetic storm would drive currents into the same path of least resistance that nearly destroyed Hydro-Quebec in 1989. And here's the connection I need you to carry forward. Those transformers aren't designed for the internal magnetic complexity of a Cannibal CME. They're stress-tested against modeled single-event storm profiles. The compound, rotating, multi-reversal magnetic structure of a Cannibal event is something the protection schemes have not been calibrated for, because until this cycle, nobody had enough operational data to calibrate against. So Part 5, the storm that missed by 9 days, one more historical data point before we go deeper. Because this one haunts the people who study space weather for a living, and I think when you see the numbers, you'll understand why. July 23, 2012. NASA's Stereo spacecraft, the Solar Terrestrial Relations Observatory, a pair of satellites in heliocentric orbit designed to give a stereoscopic three-dimensional view of solar eruptions, recorded a coronal mass ejection of extraordinary power. The measured speed exceeded 2,000 kilometers per second. A typical CME travels at 400 to 500. A fast one might do 1,000. This one was moving at a velocity that would cover the Sun-to-Earth distance in under 21 hours. At that speed, the Dias-Coviar warning window compresses to something approaching 10 or 15 minutes, maybe less. For scale, that velocity is comparable to what scientists infer for the 1859 Carrington event, the most intense geomagnetic storm in the recorded history of this planet. On September 1st of that year, Richard Carrington, an amateur astronomer in Surrey, England, was sketching sunspots through his telescope when he observed something nobody had ever documented: a white light flare erupting directly from the sun's surface. He couldn't have known that the eruption was launching a cloud of magnetized plasma that would cross 93 million miles in just 17.6 hours. When the storm arrived, it drove currents through telegraph lines so powerful that operators disconnected their batteries and continued transmitting messages using the storm itself as a power source. Auroras blazed as far south as the Caribbean and Colombia. In the northeastern United States, the night sky was bright enough to read a newspaper. Ice core analysis suggests this event was at least twice as strong as any other geomagnetic storm in 500 years. The 2012 CME crossed Earth's orbital path, but Earth wasn't there. The planet had occupied that exact position roughly 9 days earlier. 9 days is what separated modern civilization from what multiple serious institutional analyses have described as a potentially catastrophic infrastructure event. A Lloyd's of London risk assessment estimated that a Carrington-class storm striking the United States today could generate economic losses of up to $2.6 trillion. The National Academies of Sciences cited a figure approaching $2 trillion, and statistical modeling, not fringe modeling, but peer-reviewed probability work suggests a 10 to 12% chance of a Carrington-class event occurring in any given decade. Across a human lifetime, that probability is not small. It is the kind of number that keeps infrastructure planners awake, the kind that sits just below the threshold of public attention, but well above the threshold of professional concern. and we have a modern reference point now that we didn't have 5 years ago. In May of 2024, active region 3664 MAUXT, the same sunspot group that would eventually produce the strongest flare of the cycle, launched multiple fast CMEs that merged in transit, hit Earth, and drove the planetary KP index to 9. G5, extreme. The first G5 classification since the Halloween storms of 2003. Auroras were visible in Mexico, in Greece, in places where millions of people saw the northern lights for the first time in their lives. The DST index dropped to negative 412 nanoteslas, and the world's power grids this time held, but the margins were visible to anyone watching the operational data. That was a Cannibal-class compound event, multiple CMEs merging, and it produced the strongest geomagnetic storm in over 20 years. The 2012 near miss was a single CME. The 2024 event was a compound. The Carrington event was likely a compound. The pattern isn't subtle. Now hold everything I've shown you. The Cannibal mechanism that merges eruptions into complex ejecta with tangled rotating magnetic fields. The January 19th storm that exceeded its forecast when a high-speed stream and a CME stacked on top of each other. The 15 to 60 minute warning window that shrinks when the incoming plasma accelerates. The 90-second cascade in Quebec, triggered not by peak storm intensity, but by a sharp magnetic transition. The Carrington-class CME in 2012 that missed the planet by 9 days and would have cost trillions if it hadn't. The question this investigation is driving toward, and I'm going to spend the next 90 minutes proving to you that it's the right question, is this. What happens when a Cannibal CME, the kind that's been occurring with increasing frequency during a solar cycle that has defied every conservative prediction, assembles a compound magnetic structure, accelerates through the merger, arrives inside the warning window that Dieskova was barely designed to provide, and delivers the kind of sharp internal magnetic transitions that Boatler's data shows can collapse a grid in under 2 minutes? That's not a hypothetical. Every piece of that scenario has happened individually. The investigation is about whether the pieces can stack, and the evidence, as we're about to see, says they already have. Part 6, the key that opens the door. Everything I've shown you so far. The Cannibal mechanism, the forecast gaps, the 90-second cascade, all of it converges on a single physical variable that most people have never heard of. And once you understand it, the entire space weather threat landscape clicks into place like a combination lock. Here's the concept first, then the name. Earth's magnetic field points roughly northward. It rises up out of the South Pole, arcs over the planet, and plunges back in at the North Pole. Picture it as a shield, an invisible dome of magnetic force that deflects the solar wind the way the bow of a ship splits water. Most of the time, that shield holds. The solar wind washes around it, the charged particles slide along the flanks, and life on the surface goes on without registering any of it. But that shield has a weakness, and it's directional. When a CME arrives at Earth, it carries its own magnetic field embedded inside it, frozen into the plasma, twisted into ropes and sheets of magnetic force. If that embedded field is pointing the same direction as Earth's field, northward, the two fields repel. The shield holds. The CME slides around. You might get some minor disturbance at the edges, some shimmer in the aurora. Forecasters sometimes call this a nothing burger. The storm that looked threatening arrives and does almost nothing because its magnetic personality didn't match. But if the embedded field is pointing southward, opposite to Earth's, the two fields connect, not repel. Connect. And when they connect, a process called magnetic reconnection tears open the daytime side of the magnetosphere. Energy pours through the breach. Charged particles flood down along field lines into the upper atmosphere, and the resulting geomagnetic disturbance can be violent. Scientists call the north-south orientation of the incoming magnetic field the B's component. Space Weather Live describes it this way: for a geomagnetic storm to develop, it is vital that the interplanetary magnetic field turn southward. Sustained values below -10 nanoteslas are strong indicators that a storm will develop. In the March 21st, 2026 G3 event, the watchers reported that the BZ dropped to negative 28 nanoteslas, and that configuration enabled efficient coupling between the solar wind and Earth's magnetic field. Think of BZ as a key. Northward B's is the wrong key. It doesn't fit the lock, and the door stays shut. Southward B's is the right key. It fits, the door opens, and energy rushes in. The deeper the southward value, the wider the door swings. And here's where Cannibal CMEs transform from an interesting curiosity into a genuine infrastructure threat. In a standard CME, one clean magnetic cloud, the B's tends to rotate smoothly. It might start northward, swing through zero, go southward, and then recover. Forecasters can read that rotation as it passes over Dieskov and predict, at least roughly, when the southward phase will hit and how deep it will go. There's a shape to it, a rhythm, something the models can work with. A Cannibal CME destroys that rhythm, because the two parent CMEs each had their own internal magnetic structure, their own flux ropes, their own field orientations, and the merger tangles those structures together. What comes out isn't one clean rotation, it's multiple rotations, nested and overlapping, with B's swinging between northward and southward unpredictably. The door doesn't open once and stay open. It slams open, slams shut, slams open again. Each reversal drives a fresh pulse of energy into the magnetosphere. Each pulse triggers a fresh wave of geomagnetically induced currents on the ground. Now picture what the forecaster at SWPC in Boulder sees on their real-time solar wind display when a Cannibal CME washes over Dieskov. In a normal storm, the B's trace follows a recognizable pattern. The forecaster can see the southward turning beginning, can estimate how deep it will go, and roughly how long it will last, and can issue guidance to grid operators that says, expect sustained southward BZ for the next 2 to 4 hours. Plan accordingly. The operator adjusts load, boosts reactive reserves, maybe opens some interconnections. Manageable. In a Cannibal event, that BZ trace looks like a seismograph during an earthquake. The orientation whips from north to south and back. The forecaster can see it happening in real time at Dieskov, but the CME is right behind the data, 15 to 30 minutes behind it. By the time the forecaster registers a sharp southward swing, the swing has already hit the magnetosphere or is about to. And the next swing might reverse in 10 minutes or it might sustain for 3 hours. There is no way to know which. The internal structure of the merged ejecta doesn't broadcast its schedule. And it was exactly that kind of sharp transition, not peak intensity, but rapid change, that collapsed the Hydro-Quebec grid in 1989. Boatler's analysis makes that point inescapably clear. The system failed during a sudden magnetic field reversal, not during the storm's strongest sustained phase. A Cannibal CME doesn't just deliver one such reversal, it can deliver several. In sequence, inside the same event window, so the grid isn't facing a door that opens wider than expected, it's facing a door that keeps slamming. And each slam sends a different pulse through every transformer, every relay, every protection system that's trying to track what the storm is doing. The playbook says, monitor the storm's magnetic orientation and respond accordingly. But if the orientation is changing faster than the response time of the protection systems, the playbook falls apart. And here's what makes me sit with this differently than I sit with most space weather stories. The B's problem in a Cannibal CME isn't just an engineering challenge. It's an information problem. The people responsible for protecting the grid, the operators, the forecasters, the engineers, are making real-time decisions based on data that becomes unreliable precisely when it matters most. Dieskov reads the B's at L1, a million miles upstream. That reading tells you the orientation right now at L1. It doesn't tell you how the orientation will change over the next 30 minutes as different parts of the tangled ejecta wash past. For a clean, single CME, the evolution is smooth enough that you can extrapolate. For a Cannibal, you can't. The forecaster is flying blind through the most dangerous part of the storm. That's the setup for what I'm about to show you happens at the hardware level. because what the bees does to the magnetosphere does to the ground, and the ground does to every transformer connected to it. Part 7. What happens inside a transformer? At 2:45 in the morning, I need to take you inside the machinery now, because this is where the physics meets the metal. And if you understand what happens inside a transformer during a geomagnetic storm, you'll understand why Cannibal CMEs keep me up at night in a way that ordinary storms don't. A power transformer is, at its core, an elegant machine. It takes alternating current, it's your electricity, that surges back and forth 60 times a second in the United States, 50 in most of the rest of the world, and steps the voltage up or down by passing that current through coils of wire wrapped around an iron core. The alternating current creates a magnetic field inside the core that rises, falls, perfectly synchronized. The core is designed to operate in a narrow magnetic range. It handles the regular rise and fall the way a heartbeat handles the regular rhythm of blood flow. Steady, balanced, within tolerances. Geomagnetically induced currents violate that balance. GICs are quasi-direct current, essentially DC, with frequencies so low that they look like a flat line compared to the 60-cycle hum of the power grid. They enter the transformer through the neutral ground connection and add a steady push to the alternating magnetic cycle. Think of it as someone leaning on one side of a seesaw that's supposed to rise and fall evenly. With that extra weight on one side, the core gets shoved into a region it was never designed to enter, a state engineers call half-cycle saturation. And when a transformer core saturates on one half of each cycle, three things happen simultaneously, and every one of them is bad. First, the transformer begins consuming enormous quantities of reactive power. Reactive power is the invisible currency of the grid. It doesn't do useful work, but it's essential for maintaining voltage stability across the transmission system. A saturated transformer can absorb tens of megavars of reactive power that wasn't in any operator's load forecast. Multiply that across dozens of saturated transformers during a widespread geomagnetic storm, and the grid's reactive power reserves drain in minutes. Second, the saturated core generates harmonics, electrical frequencies that are multiples of the base 60 Hz. These harmonics propagate through the transmission system and can confuse protective relays. Relays are the automated sentinels of the grid. They monitor electrical conditions and trip circuit breakers when something goes wrong. But harmonics make good conditions look bad and bad conditions look normal. In Quebec, in '89, relay misoperation was a critical part of the cascade. The relays tripped lines that didn't need to be tripped, and once those lines were gone, the load shifted onto remaining lines and overwhelmed them too. Third, and this is the one that keeps infrastructure planners awake, the saturated core generates heat, stray magnetic flux that normally stays contained inside the core, leaks into the structural steel of the transformer tank, into the clamping hardware, into the windings. That heat builds, and the extra high voltage transformers, most vulnerable to GIC saturation, the ones operating at 345 kilovolts and above, are not commodity items. They weigh anywhere from 100 to 400 tons. They cost millions of dollars, and their manufacturing lead time is 18 months to 2 years. Let that number land. If a Cannibal CME drives GICs that permanently damage an EHV transformer, the replacement doesn't arrive next week. It doesn't arrive next month. You're looking at 1.5 to 2 years before a new one rolls off the production line, gets shipped, often by specialized railcar, because some of these units are too large for standard highway transport, and gets installed, tested, and energized. And there is no global strategic reserve of these transformers sitting in a warehouse. Every one is essentially custom built for its specific substation, wound for its specific voltage ratio, designed for its specific cooling configuration. During the gap, that 18-month to 2-year window, while you wait for the replacement, the grid has to work around the missing transformer. That means rerouting power through alternative pathways, which puts additional stress on neighboring transformers and transmission lines. In cold weather, when heating demand is high, that stress can push remaining equipment toward its thermal limits. In hot weather, when air conditioning drives peak load, Same problem. The grid operators know this. They plan for equipment outages, but they plan for one outage at a time. A transformer failing from age, from a lightning strike, from a manufacturing defect. Not multiple simultaneous failures across a wide geographic footprint, all caused by the same geomagnetic event, all hitting transformers that share the same 18 to 24-month replacement timeline. This isn't theoretical. During the same March 89 storm that blacked out Quebec, a generator step-up transformer at the Salem Nuclear Generating Station in New Jersey was permanently damaged by GIC-induced overheating. In September of that same year, transformer damage was observed at the Meadow Brook Station on the Allegheny Power System. And in November, a 138 kilovolt line on the BC Hydro System in British Columbia tripped from overvoltage protection during yet another geomagnetic event. Those were scattered incidents across a single year during a single solar cycle from storms that were powerful but not Cannibal-class compound events. The damage was manageable because it was distributed across time. A Cannibal CME delivers the forcing all at once, across every vulnerable transformer in a continental scale footprint simultaneously. Dr. Emmanuel Bernabeu of PJM, the regional transmission organization that coordinates power flow across 13 U.S. states, has described the March 1989 blackout as a wake-up call for our industry. PJM now takes geomagnetically induced currents very seriously with specific operating procedures triggered by NOAA storm warnings. FERC, the Federal Energy Regulatory Commission, has mandated reliability standards for geomagnetic disturbance preparedness. These are real improvements, but the fundamental vulnerability, the physics of half-cycle saturation, the reactive power drain, the harmonic confusion, the thermal risk to irreplaceable hardware hasn't changed since 1989. The transformers are the same design principle. The mechanism is the same. What's changed is that Cannibal CMEs deliver the kind of rapid, repeated BZ reversals that drive the saturation cycle harder and more unpredictably than any single event storm. And this is where the two threads of this investigation finally meet. The warning window is 15 to 60 minutes. The B's orientation of a Cannibal CME is unpredictable, and the hardware that the storm is trying to destroy takes 2 years to replace. That's the geometry of the risk, and it doesn't require a Carrington event to produce serious consequences. It requires a well-timed Cannibal CME with the wrong BZ profile hitting a grid that wasn't expecting the compound magnetic structure. Part 8, the atmosphere that ate 38 satellites. Now I need to show you that the grid isn't the only system in the crosshairs, because Cannibal CMEs produce a cascade that reaches far beyond the power lines, and the compound connections are what make this story genuinely frightening. On February 3rd, 2022, SpaceX launched 49 Starlink Internet satellites on a Falcon 9 rocket from Cape Canaveral. The satellites deployed at a low initial orbit between 210 and 320 kilometers altitude, where they were supposed to begin raising themselves to their operational altitude of 550 kilometers using onboard propulsion. They never got there. 38 of those 49 satellites burned up in the atmosphere. And the paper published in Space Weather by Barua and colleagues makes something clear that SpaceX's initial public statement obscured. The satellites weren't launched into a single storm. They were launched into an already disturbed space environment that persisted over several days. The deployment happened during the main phase of one moderate geomagnetic storm, and a second moderate storm struck the following day. Back to back. Compound. The same pattern. Sequential disturbances overlapping. That defines the Cannibal CME problem. Here's what I need you to hold on to. The storms that killed those satellites weren't even strong. They were classified as moderate to G1 to G2 on the NOAA scale. The kind of storms that happen dozens of times per solar cycle. The kind that barely make the news. The kind that most people would never even notice. But the satellites noticed. Because geomagnetic storms don't just drive currents through power lines. They dump energy into the upper atmosphere. Joule heating, the same process that makes a wire warm when current runs through it, occurs in the high-latitude ionosphere as the storm drives enormous electrical currents through the rarefied gas above the poles. That heat doesn't stay at high latitudes. It propagates. The thermosphere, the atmospheric layer between roughly 80 and 600 kilometers, expands. And when the thermosphere expands, the air density at satellite altitudes increases. For a satellite at 210 kilometers, right where those Starlink birds were sitting, the density increase was devastating. Research published in the journal Space Weather found that thermospheric neutral density increased by roughly 110 to 120% at comparable altitudes during the storm. Other modeling studies, including work by Dang and colleagues, showed density enhancements of 35 to 60% at the Starlink deployment altitude. The satellites, freshly deployed with their solar panels in a low drag configuration, couldn't generate enough thrust to overcome the suddenly thicker atmosphere. They spiraled down and burned. Yoshita Barua and colleagues at the Indian Institute of Science, Education and Research published a detailed analysis in 2024. Their conclusion is stark. Even moderate space weather events can conspire together with low-altitude orbital insertions and physical properties of satellites to bring about catastrophic losses. And they added something that connects directly to the Cannibal CME problem. Severe space weather can further compound such hazards by leading to loss of telemetry, loss of orbital positional knowledge, and uncontrolled satellite reorientation. Think about what that means in a world that is adding thousands of satellites to low Earth orbit every year. Starlink alone has more than 6,000 active satellites. Amazon's Project Kuiper is launching its first operational constellation. OneWeb. Dozens of smaller constellations serving everything from maritime tracking to agricultural monitoring to military communications. Every one of those satellites lives inside the thermosphere, the atmospheric layer that a geomagnetic storm can inflate like a balloon. And many orbit at altitudes where the density enhancements during a storm are proportionally larger than at the 550-kilometer parking orbit where most of these birds eventually settle. The February 2022 loss cost SpaceX an estimated $50 to $100 million in hardware alone. That was 38 satellites during a storm nobody thought was serious enough to delay a launch. Now scale that to a Cannibal CME, not G1 or G2, but G4 or G5. The kind of event that produces thermospheric density increases not of 30 to 60%, but of several 100% at low altitudes. The kind that persists for 3 or 4 days as the complex ejecta passes instead of a single afternoon. And during a Cannibal CME, with its protracted storm duration, its repeated BZ reversals driving repeated energy injections into the polar regions, its sustained heating of the thermosphere over hours or days instead of a single brief pulse, the atmospheric expansion would be larger, longer, and harder to predict than anything a moderate single-event storm produces. Thomas Berger, writing in Space Weather in 2023, modeled this explicitly. During extreme storms, comparable to the 1989 or 2003 events, thermospheric density can increase by much larger amounts than the 2022 Starlink event, and a large portion of the orbital catalog can be lost as satellite and debris tracks diverge from their predicted positions. In-track errors on the order of 100 kilometers per day at 250 kilometers altitude. That doesn't just mean satellites falling out of orbit. It means tracking services temporarily losing positional knowledge of objects in low Earth orbit, which means collision avoidance maneuvers can't be computed accurately, which means the risk of debris-generating collisions rises precisely when satellite operators are least able to respond. The grid goes down, the satellites can't hold their orbits, and the GPS signals those satellites relay begin to degrade, which brings us to the third thread. Gyax, Part 9. The signal that gets lost on the way down. I want to connect this to the ground now, to the infrastructure that you interact with every single day without thinking about it. Because this is where the compound effect of a Cannibal CME reaches into the daily life of every person reading this. Your phone knows where you are because satellites in medium Earth orbit roughly 20,000 kilometers up to air are broadcasting timing signals. GPS, the European Galileo system, China's Beidou, Russia's GLONASS. These signals travel from the satellites through the ionosphere, the electrically charged layer of the atmosphere, between about 60 and 1,000 kilometers altitude, and arrive at your receiver. Your phone compares the timing of signals from multiple satellites, calculates the difference, and triangulates your position. But those signals don't travel through the ionosphere cleanly. The ionosphere bends them, delays them, and sometimes, during geomagnetic storms, scrambles them. The technical term is ionospheric scintillation. During a geomagnetic storm, the ionosphere becomes turbulent. Irregularities in the electron density, pockets where the density is sharply higher or lower than the surrounding plasma, cause rapid fluctuations in signal strength and phase. Think of it like trying to read a sign through heat shimmer rising off summer asphalt. The sign is still there, the light is still reaching your eyes, but the image wobbles and blurs. Research on the May 2024 G5 storm, the strongest of the current solar cycle, quantified this precisely. A study published in Remote Sensing examined GNSS positioning accuracy during the storm peak. The three-dimensional positioning error nearly doubled compared to quiet conditions. During a 1-hour storm window, the maximum positional deviation increased by roughly 30%. Signal-to-noise ratio dropped by up to 13%. Cycle slips, moments where the receiver loses lock on the satellite signal and has to reacquire, increased by 5%. Those numbers might sound manageable, and for your phone's navigation app, they probably are. You'll still find the coffee shop. But GPS isn't just for directions. It is the invisible timing backbone of modern civilization, and most people have no idea how deep the dependency goes. Stock exchanges synchronize trades to GPS time. The New York Stock Exchange, NASDAQ, every electronic market in the world depends on nanosecond precision timestamps to sequence transactions. When that timing drifts, trades can be misordered, and the cascading errors across algorithmic trading systems can multiply in milliseconds. The power grid uses GPS timing to keep generators in phase across thousands of miles. The 60 Hz frequency that hums through every outlet in your house has to be synchronized across every generator feeding into the grid, and GPS provides the common clock. Air traffic control depends on precise positioning. Precision agriculture uses GPS-guided tractors and planters that operate within centimeters of their target. Autonomous vehicles, offshore drilling platforms, emergency dispatch systems, cellular network synchronization. Every one of these systems depends on GPS accuracy that degrades measurably during a geomagnetic storm. And during a Cannibal CME, the degradation would be worse and longer. Sustained energy input means sustained ionospheric turbulence. Repeated BZ reversals mean repeated surges of particle precipitation into the polar regions, which means repeated waves of ionospheric disturbance propagating toward mid-latitudes where most of the world's population and infrastructure actually sits. Research by Luo and colleagues found that during superstorms, GPS positioning errors at high latitudes reached over 1 meter, more than 6 times the quiet day error of 16 centimeters. At mid-latitudes, the degradation was smaller but still significant enough to matter for precision applications. But there's a deeper compound connection here, and it's the one that Sangeetha Abdujyothi at the University of California, Irvine identified in a 2021 paper that changed the conversation about space weather risk. The paper's title says it all: Solar Superstorms, Planning for an Internet Apocalypse. The global internet doesn't live in the cloud. It lives in cables, specifically undersea fiber optic cables that stretch across the Atlantic and Pacific, carrying almost all intercontinental communications. The fiber itself, glass, is immune to geomagnetically induced currents. Glass doesn't conduct electricity. For years, people assumed that meant submarine cables were safe from space weather. Abdujyothi's work showed why that assumption was wrong. The cables aren't just glass. Every 50 to 150 kilometers, roughly 30 to 90 miles, guessed they're equipped with electronic repeaters that amplify the optical signal so it can cross an ocean without degrading to noise. Those repeaters are powered through copper conductors running alongside the fiber, designed to operate at a constant 1 amp current. And copper conductors are not immune to GICs. When geomagnetically induced currents surge through the seabed and into those copper power lines, the voltage fluctuations can exceed what the repeaters were designed to handle. If even one repeater on a cable fails, the entire cable can go dark, and the geographic vulnerability is stark. Abdu Jyothi's analysis showed that the United States is highly susceptible to disconnection from Europe because the transatlantic cables traverse high-latitude routes where GIC intensity is greatest. Europe, while also at risk, has more resilience because its cable network includes a larger number of shorter routes. Asia, with Singapore acting as a connectivity hub, fares better. But the backbone links, the ones that carry the heaviest traffic between North America and Europe, are the most exposed. Abdu Jyothi's modeling found that during a catastrophic event with high repeater failure probability, nearly 80% of undersea cables could be affected, and an equal fraction of endpoints would become unreachable. And the repair timeline separates this from every other infrastructure failure we've discussed. A transformer can be replaced painfully slowly in 18 months to 2 years. An undersea repeater, sitting on the ocean floor at depths of up to 5 kilometers, requires a specialized cable ship and a remotely operated vehicle to locate, raise, and repair. There are roughly 60 cable ships on the planet. Most are already occupied laying new lines. Only about a third qualify as dedicated repair vessels. A global event damaging dozens of backbone cables simultaneously would create a repair bottleneck, measured not in weeks but in months. The economic impact of a single day of U.S. internet disruption is estimated at over $7 billion. Months of disruption to intercontinental connectivity would be, and this is the point where I want to be honest about the limits of what the data can tell us, genuinely unprecedented. There is no historical model for it because the modern internet has never been stress tested against a major geomagnetic event. And Google's own researchers, in a 2022 paper, confirmed the vulnerability. They monitored voltage changes in submarine cable power supplies during periods of high solar activity and found a strong correlation between geomagnetic field strength at cable landing sites and line voltage fluctuations. So hold the compound picture. A Cannibal CME arrives. The bees rotates unpredictably, slamming the magnetosphere open and shut. GICs surge through power grids, saturating transformers, tripping relays, threatening hardware that takes 2 years to replace. Simultaneously, energy pours into the thermosphere, inflating the atmosphere, increasing drag on thousands of low-orbit satellites, degrading their orbital knowledge, threatening the constellations that provide internet service and Earth observation. GPS signals degrade as the ionosphere turbulizes. And if the storm is strong enough and sustained enough, the repeaters in undersea cables face GIC-induced failures that could partition the global internet for weeks or months. No single one of those threads is speculative. Everyone has evidence, has named researchers, has published data. The question is whether they stack. And the physics says they must, because they share a common driver. The same magnetic energy that drives GICs and power lines heats the thermosphere that drags satellites down, that turbulizes the ionosphere that degrades GPS, that surges through the copper-feeding undersea repeaters. It's one hand pushing all the levers at once, and the levers aren't independent. They're connected. A grid failure in the Northeast doesn't just cut power to homes. It cuts power to data centers, to cell towers, to the very communication systems that emergency managers would use to coordinate the response. A GPS degradation doesn't just affect your phone's map. It affects the timing synchronization that keeps the remaining operational parts of the grid in phase. Each failure amplifies the others. That compound dependency, infrastructure systems that rely on each other, all vulnerable to the same geomagnetic driver, is the core of this investigation. And it's the reason I keep coming back to Cannibal CMEs specifically. Because it's not the peak strength that makes them dangerous. It's the duration. The sustained, protracted, erratically structured storm that keeps driving energy into all of these systems simultaneously, for hours, giving none of them time to recover before the next bee's reversal hits. And we haven't yet talked about what happens when you try to coordinate an emergency response while the grid is down. The satellites are degrading, the GPS is unreliable, and the internet is spotty. That's the next part of this investigation. and it's the part that I think changes how you see the distance between where we are and where we need to be. Part 10, the response that can't reach you, everything I've laid out so far, the grid, the satellites, the GPS, the cables, those are the systems that fail. But there's a second order problem that I think is actually more dangerous than any individual failure, and it's this. When all of these systems degrade simultaneously, the ability to respond to any one of them degrades too. The failures feed each other, and nobody in the response chain has a playbook for that. Let me walk you through a scenario that isn't hypothetical. It's just the logical consequence of the compound evidence we've already established. A Cannibal CME arrives. DESCO-VR picks up the shock at L1 and transmits the data to SWPC in Boulder. The forecasters see the BZ swinging violently southward. They issue a G4 or G5 warning. That warning goes out through NOAA's alert distribution system. Grid operators at regional control centers receive it and begin executing their geomagnetic disturbance operating procedures, reducing load, boosting reactive power reserves, opening vulnerable interconnections. So far, the system is working as designed, but the CME is a cannibal. Complex ejecta, the BZ doesn't hold a steady southward orientation. It reverses, swings north, swings south again, drives a second pulse of GICs just as the operators were adjusting to the first. Transformers that were operating within thermal limits during the initial southward phase get hit with a second wave of half-cycle saturation. Protection relays, already stressed by harmonic distortion, misfire. A cascade begins in a region with resistive geology, the upper Midwest, or the Appalachian Corridor, or the Canadian Shield. Lines trip, substations go dark, load transfers to neighboring systems, overloading them. And now the second order problem starts. Cell towers have battery backup, typically 4 to 8 hours, depending on the carrier and the site. After that, they go silent unless generator trucks arrive. But the dispatch system that sends those trucks depends on communication networks that are themselves running on the same battery backup. The GPS that routes the trucks is being degraded by ionospheric scintillation. Positioning errors are climbing. The receivers are losing lock on satellites. The accuracy that fleet management systems depend on is deteriorating. Emergency managers who normally coordinate through digital networks, email, messaging platforms, database systems, find those networks unreliable because the data centers powering them are either on backup generators or offline entirely. This is the compound dependency problem, and it doesn't have a precedent at this scale. Hurricane Katrina was catastrophic, but regional. The communication infrastructure outside the impact zone worked. Mutual aid could flow in from surrounding states over intact highways, coordinated through functioning phone networks, routed by reliable GPS. A Carrington-class Cannibal CME isn't regional. The GICs would flow across the entire continent simultaneously. The atmospheric drag would hit every low-orbit satellite in every orbital plane. The ionospheric disturbance would degrade GPS globally. There is no outside the impact zone to call for help from. The help is also in the zone. 3 days ago on this channel, we covered the operational readiness gap in emergency communication systems during extended infrastructure disruptions. 78,000 viewers saw that data. What I'm telling you today is that a Cannibal CME is the scenario that stress tests every gap we identified simultaneously. The communication gaps, the generator fuel supply chain gaps, the hospital backup power gaps, the water treatment plant gaps. Every single one at once, driven by the same geomagnetic forcing. And the institutional response framework isn't designed for simultaneity. NERC, the North American Electric Reliability Corporation, has Reliability Standard TPL-07, the Geomagnetic Disturbance Planning Standard. It requires transmission owners and generator owners to conduct vulnerability assessments every 60 months using a benchmark geomagnetic disturbance event definition. Under the revised TPL-07-2 standard that 4G approved in November of 2018, that benchmark specifies a spatially averaged peak geoelectric field of 8 volts per kilometer, with a supplemental non-spatially averaged peak of 12 volts per kilometer. Those are serious numbers, and the standard requires thermal impact assessments on transformers where model GIC exceeds 75 amps per phase. That's meaningful work. Hundreds of transmission owners and generator owners have now conducted these assessments for the first time. Some have identified vulnerabilities and developed corrective action plans. But the benchmark is based on a single event storm profile. It does not model the compound, BZ reversal structure of Cannibal ejecta. It does not model the cascading failure of communication systems that operators depend on to execute those corrective action plans. And the 4-year compliance period means that even the assessments mandated by TPL 07 were calibrated against a threat model that this solar cycle has already begun to overtake. I'm not saying the standard is useless. Far from it. It forced an industry that had largely ignored GIC risk since the early 90s to actually confront the data. That matters enormously. But standards are photographs. They capture the threat as understood at the moment the shutter clicked, and the sun has moved since the picture was taken. And consider the timeline of degradation if a major Cannibal CME hits during a period when the grid is already stressed, a heat wave driving peak load, for instance, or a polar vortex pushing heating demand to maximum. Cell tower batteries last 4 to 8 hours. Hospital backup generators typically carry 72 hours of fuel if fully supplied, but many facilities maintain less. Water treatment plants with electric pumps lose pressure. Traffic management systems go dark. Fuel stations can't pump because the pumps are electric. Even the truck that delivers diesel to the hospital backup generator needs fuel from a station that needs electricity to operate its pumps. The dependencies are circular, and every circle passes through the power grid. Emergency managers train for this. There are plans. There are mutual aid agreements between states and between utilities. But those plans assume that the communication infrastructure needed to execute them is functional. They assume GPS is routing emergency vehicles accurately. They assume the internet is carrying coordination traffic between agencies. A Cannibal CME degrades all of those assumptions. At the same time, it creates the emergency those systems are supposed to manage. That's the compound dependency problem in its purest form. And no tabletop exercise I've seen, and I've looked, models all of those failures simultaneously. Part 11, the geography of vulnerability. Not every grid is equally exposed, and this is where the investigation gets specific in ways that might matter to where you live. The physics of GIC vulnerability depends on 3 things: the strength of the geomagnetic disturbance, the electrical conductivity of the underlying geology, and the length and orientation of the transmission lines. You can't control the first one, but the second and third determine whether a given region is a high-risk zone or a moderate one. And the mapping, when you actually look at it, is more uneven than most people realize. Start with Quebec. The province sits on the Canadian Shield, Precambrian igneous rock, billions of years old, electrically resistive. When GICs flow through the ground during a storm, they can't dissipate easily through that rock, so they find the path of least resistance, the power lines. The 735 kilovolt transmission corridors from James Bay became the conduit because the rock beneath them wouldn't carry the current. That's why Quebec failed in 90 seconds. Not because the storm was uniquely powerful, it was powerful but not unprecedented, but because the geology concentrated the currents into the grid with brutal efficiency. That same class of resistive geology extends across a massive swath of North America. The Canadian Shield covers most of eastern and central Canada, dipping into northern Minnesota, Wisconsin, Michigan, and parts of New York. But the risk isn't confined to the Shield. The Appalachian region, from Georgia northward through the Carolinas, Virginia, and into New England, sits on ancient, metamorphic, and igneous formations that share similar resistive properties. The upper Midwest has pockets, parts of the Pacific Northwest, and anywhere you find long, high-voltage transmission lines running over resistive rock, you find the Quebec geometry, the combination that turned a geomagnetic storm into a grid collapse. It's not just the rock beneath the lines. The orientation of those lines matters too. GICs are driven by the geoelectric field induced in the ground, and that field has a direction that changes with the storm's magnetic characteristics. East-west lines are more vulnerable to north-south directed electric fields, and vice versa. The grid isn't a uniform target. It has seams and pressure points, and those pressure points are knowable. They can be mapped, modeled, and in many cases hardened with blocking devices that prevent GIC from flowing through transformer neutrals. But hardening costs money, and money follows attention. And attention for the past 3 decades has not been proportional to the risk. Consider the investment gap. After 1989, Hydro-Quebec invested approximately 2 billion Canadian dollars over 6 years hardening its grid, recalibrated trip levels, real-time magnetic storm monitoring, operating procedure changes. The system has survived every major storm since without a blackout. That's proof the hardening works. The investment paid for itself in avoided outage costs many times over. The United States, with a grid many times larger and serving a population 50 times greater, has taken a different path. FERC mandated the vulnerability assessments. NRC wrote the standards. Utilities conducted studies. Some have installed GIC blocking devices, neutral ground resistors, capacitive blocking devices at their most exposed substations. But the total investment in GIC-specific hardening across the U.S. grid is not proportional to the exposure, and the gap becomes most visible when you look at the transformer procurement question. The United States doesn't manufacture most of its EHV transformers domestically. The units that power the backbone of the transmission system, the 345 kilovolt and above transformers that are most vulnerable to GIC-driven thermal damage, are largely manufactured overseas. South Korea, Germany, Japan, Brazil. The manufacturing lead time is 18 months to 2 years, and the production capacity is limited because each unit is essentially custom engineered for its specific application. There is no shelf stock. There is no strategic national reserve of spare EHV transformers comparable to the Strategic Petroleum Reserve for oil. Several proposals have been made over the past 2 decades to create such a reserve. None have been fully funded. That means the recovery timeline from a severe Cannibal CME that damages multiple EHV transformers simultaneously isn't weeks or months. It's measured in years, and during those years, the regions served by those transformers operate in a degraded state, reduced capacity, reduced redundancy, reduced ability to handle the next storm, or the next heat wave, or the next ice storm. And the most vulnerable populations aren't the ones making the headlines. Urban centers have infrastructure redundancy, more substations, more interconnections, more backup systems, more repair crews per mile of line. Rural communities served by long radial transmission corridors with limited interconnection are exposed in a way that most risk analyses undercount. If the single EHV transformer serving a rural distribution area is permanently damaged by GIC-driven thermal overload, there may be no alternative path to route power in. That community goes dark, and it stays dark until a 400-ton replacement arrives from a factory on another continent. The human cost of that timeline, in a community without backup generation, without stockpiled supplies, without redundant water treatment, is not abstract. It's visceral. The international picture is equally uneven. Northern Europe, Scandinavia especially, has been at the forefront of GIC research and operational mitigation for decades, precisely because high-latitude grids are the most magnetically exposed. Finland, Sweden, and Norway operate extensive magnetometer networks and real-time GIC monitoring systems integrated into their grid operations. The United Kingdom's National Grid Company has published detailed GIC management frameworks and invested in transformer monitoring. These countries took the 1989 event as a direct warning and acted on it. But large parts of Asia, Africa, South America, and the developing world have little to no operational space weather monitoring capability. India, with a grid serving over 1 billion people, has been expanding its GIC research, but is still in early stages of operational integration. Much of sub-Saharan Africa, Southeast Asia, and Central America has no GIC monitoring infrastructure at all. A Cannibal CME doesn't check whether your grid has a mitigation plan before it drives currents into your transformers. And the populations with the least protection are often the ones with the least capacity to absorb and recover from extended outages. The ones without backup generators, without stockpiled food and water, without the institutional depth to mount a recovery operation while the grid is down. So the implications aren't abstract. They're geographic. They're demographic. They're about who has hardened their grid and who hasn't, who has real-time monitoring and who is flying blind, who has spare transformers in strategic reserve and who will be waiting 18 months for a replacement that has to be manufactured in South Korea or Germany and shipped across an ocean that may have lost some of its submarine cable connectivity to the same storm that took down the grid. The disparities map almost perfectly onto existing disparities in infrastructure investment and emergency management capacity. A Cannibal CME wouldn't create new inequalities. It would amplify every one that already exists. Part 12. The conspiracy that's wrong and the explanation that's worse. I want to address something directly now, because every time space weather makes the news, the same claims surface in the comments section, in social media threads, in emails that people send to this channel. And the people making those claims, at least most of them, deserve a real answer. Not dismissal, not condescension, not a hand wave about how scientists say it's not true. An actual engagement with the physics that either supports the claim or demolishes it. The claim comes in several versions, but the core assertion is that facilities like HAARP, the High Frequency Active Auroral Research Program, located in Gakona, Alaska, are being used to manipulate the weather, trigger geomagnetic storms, amplify solar events, or control populations through atmospheric modification. Sometimes the claim is specific. HAARP caused the May 2024 aurora. Sometimes it's vague. They're doing something up there. Sometimes it bleeds into adjacent conspiracy frameworks involving chemtrails, directed energy weapons, or electromagnetic mind control. I've seen these claims after every major aurora event this cycle, after every geomagnetic storm warning, after every unusual solar flare that makes mainstream headlines. And I understand, genuinely understand, the impulse behind them. When events are this extreme, this poorly predicted, and this capable of disrupting daily life, people look for explanations that involve human agency. Someone doing this to us feels, paradoxically, safer than the alternative is that nobody is in control, that a star 93 million miles away can reach into our infrastructure and switch it off, and that the institutions responsible for protecting us are running a single aging satellite as their frontline defense. The agency explanation is wrong, but the fear that drives it is legitimate, so let me give you the numbers. Because the numbers are where this claim either stands or falls, and they fall fast. HAARP's transmitter, the Ionospheric Research Instrument, is a phased array of 180 cross-dipole antennas spread across 33 acres of Alaskan tundra. It operates at a maximum radiated power of 3.6 megawatts. That is the total output of the most capable ionospheric heater ever built on this planet. It can heat a small patch of the ionosphere, roughly a few kilometers across, for brief periods, typically from less than a second to as long as 10 minutes. The effect is temporary, localized, and comparable in scale to the natural heating that occurs routinely during minor solar activity. The facility runs off 5 diesel locomotive engines that consume 600 gallons of fuel per hour at maximum power. 3.6 megawatts. Hold that number. A single coronal mass ejection releases more than 10 to the 24th joules of energy. That's a 1 followed by 24 zeros. To put those two numbers on the same scale, HAARP's own FAQ page, published by the University of Alaska Fairbanks, which now operates the facility after the Air Force transferred it to civilian control, states this explicitly. It would take HAARP over 10 billion years of continuous operation to produce enough energy to affect this naturally occurring phenomenon. 10 billion years. The sun is only 4.6 billion years old. HAARP would need to run longer than the sun has existed to match what a single CME delivers in an afternoon. Their analogy is vivid and worth repeating. It's like throwing a pebble into an ocean that is raging due to a hurricane. The pebble exists. It enters the water. It makes a splash, and the hurricane does not notice. No AA has published a formal fact check on its website confirming that the agency is not associated with HAARP, that the facility is funded by the National Science Foundation, and that it cannot modify the weather. Professor Fred Menck, an ionosphere and magnetosphere expert at the University of Newcastle in Australia, has described the weather control claim as nonsense, noting that weather at ground level is driven by geophysical effects in the troposphere and stratosphere, ARS, layers of the atmosphere many kilometers below the ionosphere where HAARP operates. The ionosphere starts at roughly 100 kilometers altitude. Weather happens below about 12. They're not the same system. They're not even close. The energy budget closes this door. It isn't close to open. But I also want to acknowledge, and I mean this seriously, why the claim persists, because the impulse behind it is not irrational, even if the conclusion is wrong. HAARP was originally a military-funded project, fused Air Force and Navy. Construction began in 1993. The facility operated under military auspices until 2014, when it was transferred to the University of Alaska Fairbanks. For 21 years, it was a Defense Department project operating in remote Alaska, studying something most people had never heard of, funded by agencies that aren't known for transparency. Military origins, plus ionospheric heating, plus institutional secrecy, plus events that seem inexplicable, equals a conspiracy narrative that practically writes itself. And social media amplifies that narrative with frictionless efficiency every time the sun does something dramatic. After the May 2024 G5 storm, HAARP had to publish a dedicated FAQ specifically addressing whether they caused the aurora. The people sharing these claims aren't stupid. Many of them are responding to a genuine and legitimate frustration. The sense that powerful events happen, that explanations are inadequate, and that institutions have earned skepticism. That frustration deserves engagement, not dismissal. But here's where the conspiracy framing gets unexpectedly relevant. Not because it's right, but because the actual science of ionospheric coupling that HAARP studies is genuinely important to the Cannibal CME threat. HAARP's research has contributed to understanding how solar energy transfers into the ionosphere, how that energy heats the thermosphere, and how those processes affect satellite drag, radio propagation, and GPS accuracy. The very mechanisms this investigation has documented, ionospheric scintillation, degrading positioning accuracy, thermospheric expansion, dragging down satellites, GIC-driven disruption of power systems, are the mechanisms HAARP researchers study when they artificially perturb a small patch of the ionosphere and measure the response. Understanding those mechanisms better is not a weapon. It's a diagnostic tool. It's part of the path toward predicting and mitigating the compound effects that Cannibal CMEs deliver on a planetary scale. So the conspiracy explanation is wrong. Completely, demonstrably, physics-burstingly wrong. But the actual explanation, that a star 93 million miles away can disable civilization's infrastructure through a mechanism most people have never heard of, and that the warning system protecting against it consists of a single aging satellite and a community of dedicated but underfunded forecasters, is more alarming than any conspiracy. The real human fingerprint on this problem isn't a secret weather weapon in Alaska. It's 40 years of underinvestment in space weather monitoring infrastructure. It's a grid-hardening gap measured in billions. It's a transformer procurement pipeline with no strategic reserve. It's the institutional habit of preparing for the last disaster rather than the next one. That's the story the conspiracy distracts from. And it's a story with antagonists that are a lot more mundane than a radio array in the tundra. Appropriations committees, procurement timelines, cost-benefit analyses that discount low-probability events, and the basic human difficulty of taking seriously a threat that hasn't fully materialized in living memory. Part 13, The Pattern Across Centuries. I want to pull back now and show you a pattern that becomes visible only when you look at space weather across a longer timescale than any single solar cycle. Because the Cannibal CME threat isn't new. What's new is the density of the infrastructure it can reach. And the historical record, when you actually trace the evidence, tells a story that the modern data alone can't. The Carrington event of 1859 was almost certainly a compound event. In late August and early September of that year, Richard Carrington observed his famous white light flare on September 1st. But the geomagnetic disturbances had already begun days earlier. a major storm on August 28th produced widespread aurora and telegraph disruption. Then the September 1st eruption followed, and the CME it launched arrived in just 17.6 hours. That transit time is extraordinary. It implies a velocity exceeding 2,000 kilometers per second, and it strongly suggests the interplanetary medium had been preconditioned by the earlier eruption. The first event swept the corridor clean. The second rocketed through. That sequential clearing and acceleration is the Cannibal mechanism, documented 167 years before anyone had a name for it. The March 1989 event that collapsed Quebec's grid followed the same pattern. Sequential CMEs from active region 5395, the first on March 10th, the second on March 12th. Bodler's 2019 analysis confirmed that the blackout-triggering magnetic disturbance occurred during a sudden field transition, not during peak storm intensity. The compound arrival created the sharp rate of change signature that overwhelmed the grid's protection systems. Compound event. Sharp transitions. SIME physics. The May 2024 G5 storm, the strongest event in over 2 decades, involved multiple CMEs from active region 3664 merging in transit. Cannibal class compound ejecta. The KP reached 9. The DST dropped to negative 412 nanoteslas. Auroras were photographed in Mexico, in Greece across the Caribbean. The grids held, but the event confirmed that compound CME mergers are the mechanism behind the most extreme modern storms. And the April 2025 Cannibal CME, 2 eruptions launched in rapid succession from the same region, absorbed and merged en route ease, drove geomagnetic conditions to G4 after NOAA had forecast G3. The compound arrival exceeded the forecast. Again, the pattern repeats. Go deeper still. Ice core records and tree ring studies have identified events that dwarf everything in the modern observational era. The Miyake event of 774 CE was identified through an abrupt spike in carbon-14 concentration in tree rings from that year, a signature that can only be produced by intense solar particle bombardment of Earth's atmosphere. The spike was so large, so sudden, that when Fusa Miyake and colleagues first published the finding in 2012, the solar physics community had to reckon with the possibility that the sun was capable of far more extreme behavior than anything in the 4 centuries of telescopic observation. Subsequent research has identified additional Miyake-class events in 993 CE, 660 CE, and approximately 7770 BC. These weren't minor variations. They were discrete, sharp, and enormous. The 774 event may have been 10 to 100 times more intense than anything in the modern satellite era, depending on the modeling assumptions used to convert tree ring isotope data into solar particle flux estimates. If a Miyake-class event occurred today, driving GICs of unprecedented magnitude, inflating the thermosphere to altitudes that would drag down entire satellite constellations, ionizing the atmosphere to a degree that would black out radio communications globally for hours or days, the consequences would exceed anything the insurance industry, the grid reliability standards, or the space weather forecasting community has been designed to handle. The models simply don't go that high. The standards weren't written for that world, and the probability of such an event, while low in any given year, is not 0 over a century or a millennium. The proxy record says they happen. We just haven't had one since we became a technological civilization. The pattern across these events tells a story that I think deserves more attention than it gets. The worst geomagnetic storms in the historical and proxy record are not single-shot events. They are compounds, sequential eruptions from hyperactive regions merging in transit, delivering complex ejecta with tangled magnetic fields. The Carrington event, the 1989 storm, the 2024 storm, every one of them. And the sun, as of today, is still producing the hyperactive regions, the flare factories like AR4366, that launch the kind of back-to-back CMEs that merge into Cannibal ejecta. And here are the questions the historical pattern forces us to ask. If compound events are the signature of the most extreme storms, Why is the benchmark standard for grid protection still modeled on a single event profile? Why doesn't TPL-007 include a compound BZ reversal scenario that tests the grid's response to internal magnetic complexity? Why doesn't the vulnerability assessment framework account for simultaneous degradation of the communication, GPS, and internet systems that operators depend on to execute their corrective action plans? Those aren't rhetorical questions. They have answers. The answers involve institutional timelines, the genuine scientific difficulty of modeling compound ejecta internal structure, the political economy of multi-billion-dollar infrastructure investments, and the simple fact that the science of Cannibal CME behavior is still developing. Each new event teaches the research community something the models didn't previously capture. But the gap between the threat and the standard is real. It's measurable. And the sun doesn't wait for the standard to catch up. The evidence base is assembled. The compound picture is complete: grid, satellites, GPS, cables, response systems, geographic vulnerability, historical precedent. In the final stretch of this investigation, I'm going to present 3 interpretations of what all of this evidence means: the most reassuring, the most supported by the literature, and the most concerning, and let you weigh them against each other. The data doesn't tell us which interpretation is correct. What the data does tell us is what each one costs if it turns out to be wrong. Part 14. The reassuring interpretation. I promised you 3 ways to read this evidence, and I meant it when I said the first interpretation, so the most reassuring one, would get a fair hearing, because it deserves one. It accounts for real data, and the people who hold this view aren't naive. They're looking at the same evidence and weighing it differently. Here's the case, and I want you to hear it fully before we move to the other 2, because this interpretation has more evidence behind it than most people in the space weather anxiety space are willing to acknowledge. The modern grid has been hit by significant geomagnetic storms and survived. The May 2024 G5 event, the strongest in over 2 decades, driven by Cannibal-class compound ejecta from active region 3664, produced a KP of 9, a DIST of negative 412 nanoteslas, and auroras visible in Mexico, in Greece, in Colombia. Millions of people around the world saw the northern lights for the first time. It was exactly the kind of compound event this investigation has been describing. Multiple CMEs merging in transit, complex ejecta, sustained forcing, and the world's power grids held. No cascading blackouts. No reported permanent transformer damage. The lights stayed on in Quebec. The lights stayed on everywhere. That is not a minor data point. It's the most significant single piece of evidence in this entire investigation for the reassuring case. The stress test happened. The grid passed. The reassuring interpretation says the grid has hardened since 1989. Quebec spent $2 billion proving it could be done, and every major storm since has validated the investment. First mandated NERC's TPL-007 standard, requiring vulnerability assessments every 60 months at benchmark forcing levels of 8 to 12 volts per kilometer. Hundreds of utilities have conducted those assessments. Protection relay settings have been recalibrated to higher harmonic tolerance. Operating procedures have been updated to reduce load transfers and suspend switching during storms. The industry learned from Quebec. It acted on what it learned, and pretending otherwise would be dishonest. This interpretation extends to the satellite domain. The Starlink loss in February 2022 was a deployment altitude problem. Those satellites were at 210 kilometers far below their operational orbit in a minimal drag configuration that couldn't generate enough thrust to overcome even a moderate atmospheric density increase. Operational Starlink satellites at 550 kilometers were completely unaffected. SpaceX and other constellation operators now factor space weather forecasts into launch timing. The vulnerability was real, but bounded, specific, and correctable through operational procedure rather than hardware redesign. And on the submarine cable front, this interpretation points to a crucial distinction between modeled worst-case scenarios and operational reality. Abdu Jyothi's 2021 paper modeled catastrophic failure probabilities. Google's 2022 research confirmed the physical mechanism for voltage correlations in cable power feeds during solar activity, but did not observe actual repeater failures. The cables have been operating through solar cycle 25's most active phase without reported space weather-driven outages. Modern cable systems include design margins. The catastrophic internet partition scenario requires a storm more extreme than anything in the modern record, and the probability of such an event in any given year remains low. The reassuring reading summarizes like this: the risks are real but manageable. The institutional response has been slow but directionally correct. The probability of a Carrington-class Cannibal CME in any given decade is 10 to 12% DERs, which means there's an 88 to 90% chance it doesn't happen this decade. Investment should continue, standards should evolve, but the measured, incremental approach is working. Panic is not warranted. Vigilance is. This interpretation is not wrong. It is fair. It is evidence-based. And if you choose to hold it, you have substantial data on your side. But it requires you to accept several assumptions that the deeper evidence makes uncomfortable. It requires you to assume that the 2024 event represented something close to the upper bound of what a Cannibal CME can deliver, even though the Carrington event was substantially stronger and the Miyake events stronger still. It requires you to assume that grid hardening has been uniformly distributed, even though the data shows enormous regional disparities in investment, with rural communities and developing nations far less protected. It requires you to assume that the compound dependency cascade I've documented, grid plus satellites, plus GPS plus internet degrading, simultaneously can be managed through existing institutional frameworks that have never been tested against that specific failure mode. And it requires you to trust that a warning system consisting of a single satellite operating past its design life will continue performing when the sun delivers its most extreme output. Those assumptions may hold. They are reasonable assumptions to make, but they are assumptions. And the next interpretation starts from the question of what happens if one or more of them doesn't. Part 15. The interpretation. The evidence most directly supports. The intermediate interpretation. The one that sits closest to where the published peer-reviewed literature actually points, says this: the Cannibal CME compound threat is real, systematically underestimated by current standards, and likely to produce a significant infrastructure event within the next 2 to 3 solar cycles. Not civilization ending, not a permanent internet apocalypse, but a regional grid failure affecting millions of people for days to weeks, with satellite and GPS degradation compounding the response, in an event that exceeds the TPL-07 benchmark because its compound magnetic structure wasn't part of the design basis. The evidence for this interpretation is substantial, specific, and comes from named researchers with serious institutional weight. Start with the grid. Boatler's 2019 analysis established that the Quebec blackout was triggered by rate of change dynamics, sharp magnetic transitions, not peak storm intensity. The grid failed during a sudden BZ reversal, not during the strongest sustained southward phase. Cannibal CMEs, with their complex internal ejecta structure of tangled flux ropes and nested magnetic field rotations, are specifically optimized to produce those transitions. They deliver multiple sharp reversals inside a single event window. The mechanism that collapsed Quebec in 90 seconds is the default output of a Cannibal CME. Every one of them. Move to the satellites. Barua and colleagues demonstrated in their 2024 space weather paper that even moderate geomagnetic storms, G1 to G2, the kind that barely make the news, can conspire with orbital conditions to produce catastrophic satellite losses. 38 Starlink satellites destroyed by storms that weren't even classified as strong. A Cannibal CME delivering sustained thermospheric heating over days rather than hours would extend and amplify that drag effect across entire mega constellations. The vulnerability isn't theoretical. It's been demonstrated. The only question is scale. Move to the cables. Abdujyothi's 2021 SIGCOMM paper established the submarine cable repeater vulnerability as a credible threat vector for extreme events. Google's Castellanos and colleagues confirmed the physical mechanism in 2022 with operational measurements, voltage fluctuations in cable power feeds, correlating directly with geomagnetic field strength at landing sites. The cables have survived the current cycle so far, but the current cycle hasn't delivered a Carrington-class event. The mechanism is confirmed. The threshold hasn't been crossed. Yet. And the forecasting gap. The NOAA SWPC data from January 19, 2026 demonstrated in real time that compound solar wind conditions, a coronal hole, high-speed stream overlapping with a CME arrival, can produce observed storm intensities exceeding the forecast by a full G level. Observed KP of 8 against a forecast of 6.67. That's a 1-level miss on a 5-level scale. For a grid operator making protection decisions at 2 in the morning, based on that forecast, a 1-level miss can be the difference between a managed event and a cascade. The statistical framing matters here too. The 10 to 12% per decade probability that gets cited for Carrington-class events is an estimate of extreme geomagnetic storms generally. It doesn't separately account for the compound nature of the threat. It doesn't distinguish between a clean, single CME with predictable BES behavior and a Cannibal CME with complex ejecta delivering unpredictable reversals. The actual probability of a storm that exceeds current response frameworks may be higher than the headline number suggests because the frameworks were designed for a simpler kind of storm. This interpretation says the most likely outcome of a well-timed Cannibal CME in the current or next solar cycle is a Quebec-scale event. Regional, severe, recoverable, but more widespread and more complex than 1989 because the grid is more interconnected. The dependencies on satellites and GPS are deeper, and the communication systems that coordinate the response are themselves vulnerable. The grid fails in the most geologically exposed regions. Transformer damage extends recovery beyond what emergency fuel supplies can bridge. GPS degradation complicates vehicle routing and grid synchronization. The internet experiences disruption, not the full partition Abdou-Jyoti modeled, but enough to slow coordination during the critical first 72 hours when decisions matter most. The researchers I've engaged with on this topic, the forecasters at SWPC, the GIC modelers, the grid vulnerability analysts, most of them land somewhere in this interpretation. Not dismissive, not alarmist. Specifically concerned about a compound threat that current standards aren't fully calibrated for, and quietly frustrated that the investment needed to close the gap keeps getting deferred because the last storm wasn't quite bad enough to force the issue. That's part 16, the concerning interpretation. The third interpretation is the one that keeps certain researchers awake at 3 in the morning, and I owe it the same rigor I gave the other two, because it is grounded in evidence, not speculation, and dismissing it as alarmism would be intellectually dishonest. This interpretation says a Carrington-class Cannibal CME, compound ejecta, extreme velocity, sustained southward BZ with multiple sharp reversals, hitting a grid that is simultaneously experiencing peak load conditions during a heat wave or cold snap would produce a cascading infrastructure failure that exceeds the response capacity of existing institutions. Not because the institutions are incompetent, not because the people working in those institutions aren't dedicated and skilled, but because the failure mode is simultaneous across domains that current planning treats separately, and the dependencies between those domains are circular in ways that no exercise has fully tested. The evidence path runs like this. The Carrington event's CME arrived in 17.6 hours, implying a velocity exceeding 2,000 kilometers per second. At that speed, Dieskova warning window shrinks to somewhere between 10 and 15 minutes, possibly less. A Cannibal CME at Carrington speeds, carrying complex internal BZ structure with multiple magnetic reversals, would give grid operators almost no time to interpret the field data, model the expected GIC pattern, determine the appropriate load reduction strategy, and execute protection actions across a system spanning thousands of miles before the first GIC pulse arrives. The first pulse saturates transformers. Minutes later, the BZ reverses. A second pulse arrives, catching the grid in the middle of its response to the first. Protection relays, already stressed by harmonic distortions from the first saturation event, misfire during the second. Lines trip. Low transfers overwhelm remaining capacity. Cascade. Now compound that with everything else the same magnetic forcing drives simultaneously. The thermosphere inflates as energy pours into the polar regions. Satellite drag increases across every orbital plane. Positional knowledge of thousands of objects in low Earth orbit degrades as orbital predictions diverge from reality. GPS accuracy falls as the ionosphere turbulizes, not by a little, but by factors of 6 to 10 times at high latitudes, based on the LUO data. Communication satellites in geostationary orbit experience surface charging events that can trigger anomalies or protective shutdowns, and submarine cable repeaters face the voltage surges that Abdu Jyothi and Castellanos documented. With the highest latitude transatlantic routes, the ones carrying the heaviest intercontinental traffic, facing the greatest GIC exposure. The concerning interpretation takes Abdu Jyothi's 80% cable failure scenario seriously. Not as a guaranteed outcome, no responsible researcher would claim that, but as a physical possibility for an extreme event whose probability is low in any given year but non-negligible over a human lifetime. And it asks the question that I think the compound evidence demands. What happens when the power grid, the satellite constellation network, and the intercontinental internet all degrade within the same 72-hour window? The answer, and this is the part that makes this interpretation genuinely sobering, is that no existing emergency management framework has been designed, tested, or exercised against the simultaneous failure mode. Mutual aid agreements assume communication systems work. Grid restoration procedures assume the supply chain operates. The supply chain assumes the internet coordinates it. Financial systems assume GPS provides timing. Each system's recovery plan assumes the other systems are available. When they all degrade at once, the plans don't fail because they're bad plans. They fail because their assumptions fail first. Lloyd's of London estimated $2.6 trillion for a Carrington-class grid event. That estimate covers power system damage and economic disruption from electricity loss alone. It does not include satellite constellation losses, GPS-dependent economic disruption across aviation, finance, agriculture, and logistics, or the cost of internet connectivity degradation. The true cost of the compound scenario, all threads degrading simultaneously, has not been modeled by any major institution because the modeling frameworks don't yet integrate across those domains. The grid models don't talk to the satellite models. The satellite models don't talk to the cable models. Nobody has built the compound model yet. The compound picture exists in the research literature, in Boatler, and Abdu Jyothi, and Berger, and Barua, and Castellanos, but it has not been assembled into a single integrated risk assessment. That absence is itself a vulnerability. I need to be clear. This interpretation is not a prediction. It is not what I'm telling you will happen. It is a physical possibility. Every element of it has occurred individually. The question is whether they stack in a single event. The physics says they can because they share a common driver. Whether they will, in any given event, depends on the CME's velocity, its internal magnetic structure, the state of the magnetosphere at arrival, the geology under the exposed grids, and the preparedness of the operators in the critical first minutes. The uncertainty is real and irreducible with current observational capability. But so is the exposure. Chat, part 17, what we know and what we don't. Let me lay this out as cleanly as I can, because after 2 hours of evidence, you deserve a clear accounting of where the certainty lives and where it doesn't. No hedging, no vagueness, just the line between what the data has established and what remains genuinely open. What we know, confirmed, peer-reviewed, operationally demonstrated, Cannibal CMEs are real, recurring, and more frequent during solar maximum. The mechanism, a faster CME overtaking and absorbing a slower one from the same active region, has been observed directly, modeled by NASA's Scientific Visualization Studio, and confirmed during multiple events in solar cycle 25, including the May 2024 G5 storm and the April 2025 G4 event. This is not a theoretical construct. It is observed physics. The internal magnetic structure of Cannibal ejecta is more complex than that of single-event CMEs. Multiple BZ reversals, tangled flux ropes, unpredictable magnetic field orientation, changes within a single event window. This is established in the heliophysics literature, confirmed by in situ measurements at L1, and is the core reason these events present a different challenge to grid operators than standard CMEs. DSCOVR provides 15 to 60 minutes of warning depending on CME speed. That window compresses for faster events. DSCOVR has been operating for more than 11 years against a 5-year design life. There's currently no operational backup spacecraft at L1. If DSCOVR fails, the warning window drops to 0. Grid operators would rely entirely on solar observation and propagation models, which the January 2026 data showed can underestimate storm intensity. Geomagnetically induced currents, driven by geomagnetic storms, can saturate power transformers through half-cycle DC bias, causing reactive power drain, harmonic generation, relay misoperation, and thermal damage to transformer cores and structural components. This has been demonstrated operationally in the 1989 Quebec blackout, documented in multiple subsequent events, including the 2003 Halloween storms, and is the physical basis for NRC's TPL-007 reliability standard. EHV transformer replacement lead times are 18 months to 2 years. Most are manufactured overseas. There is no strategic national reserve in the United States. This is a supply chain fact, not a modeling assumption. Geomagnetic storms heat the thermosphere and increase atmospheric drag on satellites in low Earth orbit. The February 2022 Starlink loss, 38 of 49 satellites destroyed during moderate G1 to G2 storms, confirm this at operationally significant levels. Extreme storms would amplify the effect by factors of several. Ionospheric scintillation during geomagnetic storms degrades GPS and GNSS positioning accuracy. This has been measured and published for every major storm in the satellite era. Errors at high latitudes can exceed 1 meter during superstorms. Mid-latitude degradation is smaller but measurable and affects precision applications. Submarine cable repeaters are powered by copper conductors that are vulnerable to GIC voltage surges. Google's Castellanos and colleagues measured voltage fluctuations in operational cable power supplies correlated with geomagnetic activity. The catastrophic failure threshold has not been observed in the modern era, but is physically achievable at extreme forcing levels. What we don't know, genuinely uncertain under active research. The exact internal magnetic structure of any specific Cannibal CME before it arrives at DSCOVR. Current propagation models. The WSA NLIL model that SWPC uses operationally can estimate arrival time and approximate speed with reasonable accuracy. They cannot reliably predict BZ orientation, the number of internal magnetic reversals, or the timing and depth of southward excursions. That information becomes available only when the ejecta reaches L1. At that point, the CME is 15 to 60 minutes from Earth. Whether the compound dependency cascade would actually play out as the physics suggests. We have never observed a simultaneous degradation of power grids, satellite constellations, GPS accuracy, and internet connectivity from a single geomagnetic event. It is possible that human adaptation, institutional improvisation, and built-in system resilience would blunt the compound effect in ways the physics alone can't predict. We don't know because we've never tested it. And you can't test it with a tabletop exercise because the critical variables are the ones that only emerge under real operational stress. The probability of a Carrington-class Cannibal CME within any specific time frame. The 10 to 12% per decade estimate applies to extreme geomagnetic storms as a class. The conditional probability of that storm arriving as a Cannibal with worst-case BZ structure, the specific configuration that maximizes grid damage, is not well constrained in the literature. It could be lower than the headline number, or it could be that most Carrington-class events are compound by nature, which would make the headline number approximately right. The proxy record suggests compound events dominate the extreme tail of the distribution, but the sample size is small. Whether the NRC TPL-07 benchmark is sufficient for the compound threat. The standard was designed using a single event geomagnetic disturbance profile. Whether it adequately captures the rate of change dynamics produced by Cannibal ejecta with multiple Beasley reversals is an open and important research question that has not been definitively answered. What specific observations would distinguish between the three interpretations? If the next G4 or G5 event arrives as a documented Cannibal CME with complex Beasley structure and the grid handles it without significant transformer damage or regional blackout that materially strengthens the reassuring interpretation, it would mean the hardening investments that have achieved sufficient resilience against compound events, not just simple ones. If a Cannibal CME produces a regional blackout comparable to or exceeding Quebec 89 in scale, with measurable GPS and satellite degradation complicating the emergency response, that confirms the intermediate interpretation and should trigger an immediate revision of TPL-007 to include compound event profiles. If a Carrington-class Cannibal event produces simultaneous grid failure, satellite constellation disruption, GPS degradation, and submarine cable impacts in a single event window, that validates the concerning interpretation and should trigger a fundamental reassessment of space weather preparedness across every infrastructure domain. We are watching for all three, and the data will arrive on the sun's schedule, not ours. Part 18, the quiet part. This is the section where the energy comes down, where the data recedes and the voice gets quieter, because after everything I've shown you, quiet is what the evidence deserves. Not urgency, not a call to action, just an honest reckoning with what we've seen and what comes next. I've spent 2 hours showing you something that most people haven't fully reckoned with. Not because the information isn't available. Almost all of it is published in peer-reviewed journals, posted on government websites, and accessible to anyone with an internet connection and the patience to read it. But because the pieces live in separate worlds. The grid researchers at EPRI and NERC know about transformer saturation. The satellite researchers at NASA Goddard and the European Space Agency know about atmospheric drag. The ionospheric scientists at universities in Norway and Finland and Colorado know about GPS scintillation. The network engineers at Google and the submarine cable industry know about repeater vulnerability. Each community understands its own domain deeply, but the compound picture, all of it together, driven by the same solar magnetic event, degrading simultaneously, feeding back into each other through dependencies that cross every domain. Boundary? That picture exists only when you connect the threads. And connecting those threads is what this channel was built to do. I don't know when the next Cannibal CME will arrive. Nobody does. Solar cycle 25 is expected to continue declining through 2027 and 2028, which sounds like the threat should be easing. But the declining phase of a solar cycle is historically when some of the most powerful individual eruptions occur. The remaining active regions tend to be large, magnetically complex, and capable of launching the kind of rapid-fire eruptions that merge in transit. The Carrington event occurred during the declining phase of solar cycle 10. Some of the most intense flares of cycle 25 are the X9 from October 2024, the X8.1 from February 2026 have come after the predicted peak. The sun doesn't wind down on a schedule. What I know, what the evidence tells me with confidence, is that the conditions that produce Cannibal CMEs are present in every solar cycle, become more frequent during maximum and early decline, and are currently active. The warning system is a single spacecraft operating past its intended lifespan. The infrastructure it protects is more interconnected, more dependent on systems that share the same geomagnetic vulnerability, and more globally integrated than during any previous solar maximum in human history. The reassuring interpretation has real evidence behind it. The grid survived 2024. The concerning interpretation has real physics behind it. The compound cascade is physically achievable. The intermediate interpretation, the one I believe sits closest to where the science actually is, says we're underprotected for a specific class of event that the historical record says will recur, What happens next depends on two things: what the sun does and what we do before it does it. There are specific, concrete, achievable steps that would materially reduce the risk. A Discover successor mission at L1EA's already in planning stages at NOAA as the Space Weather Follow-On program would provide the continuous solar wind monitoring that the planet depends on, with modern instrumentation and a fresh design life. Accelerating that program is not exotic science, it's insurance. Expansion of the ground-based GIC magnetometer network, the kind of real-time monitoring that Scandinavia has operated for decades, would give grid operators ground truth during a storm, not just space-based estimates. Every major utility in a geologically vulnerable region should have magnetometer data feeding directly into their control room. The technology exists. The cost is modest relative to the grid infrastructure it protects. A strategic reserve of EHV transformers, even a small number of high-voltage units pre-positioned at critical substations, RE2, would cut recovery timelines from years to weeks after a damaging event. This has been proposed repeatedly. It has not been funded, and perhaps most importantly, integration of space weather scenarios into emergency management exercises at the national level, not just grid exercises that model the compound failure of power, communication, navigation, and data systems simultaneously. The kind of exercise that tests whether the mutual aid agreements work when the communication systems they depend on are degraded. Nobody has run that exercise. Until someone does, the institutional response to a Cannibal CME remains untested against the scenario it's most likely to face. None of that is science fiction. None of it requires new physics or new technology. All of it is engineering, procurement, and policy. And all of it is achievable at investment levels that are a rounding error compared to the cost of the event it would mitigate. Lloyd says $2.6 trillion for the grid alone. A Discover successor costs a fraction of that. This investigation will continue. Solar Cycle 25 is still producing hyperactive regions. The sun still has years of elevated activity ahead, even as it declines from peak. Every SWPC forecast product, every DSCO VR data stream, every active region that rotates into Earth's view with the magnetic complexity to launch back-to-back eruptions. We're watching all of it. And when this story moves, when the next Cannibal CME assembles in interplanetary space and turns toward Earth, we'll be here, with the data, with the context, with the evidence base we built today, and with the honesty that I think this topic demands from anyone who covers it. Because the sun doesn't care about the calendar. It doesn't care about the forecast. It doesn't care about the standard or the budget cycle or the procurement timeline. And the only thing standing between a Cannibal CME and the infrastructure that 8 billion people depend on is a 570 kilogram satellite, a community of dedicated forecasters working with tools that haven't been upgraded in a decade, and however much time and investment we collectively decide the warning is worth. We'll be watching.